quantum field theory, the most thoroughly tested model in the history of science. It has a calculation that, when you run it, predicts the universe should not exist. It looks at empty space and asks how much energy is hiding in the vacuum. The answer is catastrophic, so much destructive energy that spacetime should instantly crumple in on itself. The universe should annihilate itself in its first instant. The math demands nothing, a clean, absolute zero, but the telescope shows something. Galaxies, stars, you. The gap between prediction and observation isn't a small margin of error. It is a factor of 10 to the 120th power, the single largest failed prediction in all of physics. This changes the old philosophical question, why is there something rather than nothing, from a riddle into a concrete bug report from the deepest layer of reality, a specific, unresolved contradiction. A calculation that breaks when it asks the price of existence. The answer comes back as zero. Your existence is the anomaly, a glitch the equations can't explain, and right now, nobody knows why the answer isn't zero. Let's look inside that factor of 10 to the 120th power. It comes from a simple recipe. Take the zero-point energy of every quantum field at every point in space for every possible frequency and add them all up. Each quantum field acts like a collection of tiny springs. A quantum spring can never sit still. It always jitters with a minimum energy called zero-point energy, forced by Heisenberg's uncertainty principle. To get the total vacuum energy, you sum the zero-point energies of all fields, electron field, quark field, photon field, up to a maximum frequency called the Planck frequency. That sum is not just large. It is astronomically large. If you do the arithmetic, you get a number around 10 to the 93rd power grams per cubic centimeter. That is about 10 to the 120th power larger than the observed vacuum energy density, which we measure through the expansion of the universe. So the mismatch is not a subtle error, it is an abysmal failure. This discrepancy has a name, the cosmological constant problem. It is the worst prediction in all of physics. It tells us that our most successful theory of the microscopic world, when applied to the emptiness of space, produces a catastrophic answer. The universe should have either collapsed instantly or expanded so fast that no structure could form. Yet we are here. That is not a solved puzzle. It is a staring contradiction that no one has been able to resolve. In 1917, Albert Einstein stared at his own equations. General relativity had just been born, and it told him something he refused to believe. The math said the universe could not sit still. It must be either expanding or contracting. But the prevailing view, shared by Einstein himself, was that the universe was static, eternal, and unchanging. So he added a term to balance the books, a symbol he called the cosmological constant. A Greek letter, lambda, inserted to push back against gravity and keep everything frozen in place. 12 years later, Edwin Hubble pointed the Hooker telescope at distant galaxies and watched them all recede. The universe was expanding. Einstein had been wrong. He reportedly called the constant his biggest blunder. Though the exact origin of that quote is disputed, the sentiment was real. The constant was a blemish, a man-made patch for a universe that didn't need one. It was cast out of the equations and treated as a historical oddity. Then came 1998. Two teams of astronomers, led by Saul Perlmutter and Brian Schmidt, were studying distant supernovae to measure how the universe's expansion was slowing down. They expected to find deceleration from gravity. Instead, they found the opposite. The expansion was speeding up. Something was pushing. The only known force that could do that was the cosmological constant. The abandoned Greek letter was resurrected, rebranded as dark energy. But here is the cruel twist. The constant we observe matching this acceleration is tiny, exactly the scale that makes the cosmological constant problem from our last chapter so devastating. The universe is accelerating, but the driving force is unimaginably smaller than quantum physics says it should be. Einstein's constant is back from the dead, and it brought the worst prediction in all of physics with it. And that worst prediction isn't a mistake in the math. It's a mandatory output of quantum field theory, a core result you cannot avoid. Inside that theory, every field is a grid of tiny quantum springs. Heisenberg's uncertainty principle says no spring can ever sit still. Each one jitters with a minimum energy, half a quantum proportional to its frequency. Higher frequency, more energy. Now, to get the vacuum energy of a single field, you must add up the jitter of every spring at every possible frequency. There's no internal stop sign. You sum from the lowest note all the way to the Planck frequency, the maximum where our laws shatter. Cap it there, and you already get a colossal number. Then you repeat for every known field. Electron, quark, photon, gluon, every particle. Each field has its own set of springs. Add them all together. The result is a vacuum energy density around 10 to the 93rd grams per cubic centimeter. This isn't a speculative guess. This sum follows directly from quantizing fields. Quantum field theory gives you no knob to turn it down, no escape hatch. You can try to subtract the infinity through renormalization, but that forces you to set the final value by hand, matching observation. That's not a prediction, it's a reset. The theory itself offers no reason for the number to be small. So the same theory that gives us lasers and transistors also says empty space should be astronomically dense. Dense enough to instantly shred the universe. But when we measure the vacuum energy through cosmic expansion, we find a value 120 orders of magnitude smaller. The gap is not subtle. It's the worst failure of quantitative prediction in science. The math is rigid. The universe is silent, and between them lies a contradiction no one has cracked. Here's the pattern that quietly haunts physics. The cosmological constant isn't alone. There are at least 26 fundamental constants and initial conditions that must fall within absurdly narrow margins for any stars, planets, or chemistry to exist. Change almost any of them by a hair, and the universe becomes a lifeless wasteland of boring particles. Take the strong nuclear force. In the 1950s, astronomer Fred Hoyle predicted that carbon must possess a very specific energy resonance for it to be made inside stars. Without it, beryllium would decay before fusing into carbon, and the stellar assembly line would stop. Later experiments found that resonance exactly where Hoyle said it had to be. But here is the catch. If the strong force were just 4% weaker, that resonance vanishes, and 3/4 of all carbon production disappears. 4% stronger, and the carbon itself burns straight into oxygen. The window is a sliver. Now look at the fine structure constant, the number that governs how tightly electrons bind to atoms. Currently it sits at roughly 1/137. Turn it up just 4%, and no carbon forms at all. The entire pathway collapses. Turn it down a comparable amount, and protons and neutrons would not hold together. No atoms, no chemistry, no structure. The list runs deeper. The mass difference between the up and down quarks, the ratio of the proton mass to the electron mass, the strength of gravity relative to electromagnetism. Every one of these knobs appears set with surgical precision to allow complexity to emerge. The cosmological constant is just one dial on this board. Set it 10 powers larger, and the universe expands so fast that no galaxies form. Set it negative, and it crunches back in microseconds, so the same puzzle stares back at you from every corner. The dials are too precise to ignore. The math says the universe shouldn't work, but it does. The question left on the table is whether that silence is a coincidence, a clue, or something else entirely. If you rewind the universe to the first trillionth of a second, you should find a perfectly balanced sea of matter and antimatter. Exactly equal numbers. That is what the laws of physics demand. Energy turns into pairs, a particle and its mirror opposite. That rule has no exceptions. So as the cosmos cooled, every particle should have met its twin and vanished, leaving behind only pure light. A universe of photons with nothing else. Yet you exist, your chair exists. The stars exist. Somewhere something broke the symmetry. The imbalance is tiny but absolute. For every 1 billion antimatter particles, there were 1,000,000,001 matter particles. That single extra particle per billion survived, and everything we see is built from that 1 in a billion leftover. The question is, what caused the imbalance in the first place? In the 1960s, physicist Andrei Sakharov laid out 3 conditions needed for matter to win. First, some process must violate baryon number, the count of protons and neutrons. Second, the laws of physics must treat matter and antimatter differently, a property called CP violation. Third, those reactions must happen out of thermal equilibrium, so the reverse reaction can't restore balance. The standard model includes CP violation, but it is far too weak. When scientists measure it in kaons and b mesons, the effect is about 1 billion times too small to account for the cosmic surplus. You would need 1 billion times more tilt than what we see. That gap is not a measurement error, it signals missing physics. So the imbalance we live inside is a clue. Something beyond the standard model must have tipped the scales in that first chaotic moment. New particles, new forces, a new kind of CP violation we have not detected yet. The asymmetry is certain, the cause is not, and that silence, once again, is where the real story begins. So why does the universe have the precise dials that allow you to exist? The most common answer given by physicists is also the most frustrating, the anthropic principle. It sounds like a cheat code, and it might be. The weak version says that we, as observers, can only exist in a universe that allows observers. That's a selection effect, not an explanation. If the constants were different, we wouldn't be here to notice, so there's no surprise that we see fine-tuning. It's logically airtight, but it says nothing about why those constants are what they are in the first place. The strong version goes further. The universe must have life-permitting properties. That implies purpose or necessity, a teleological claim. Most physicists reject it because must is not derived from any known law. It's a statement of desire, not evidence. Here is the trouble. Picture a puddle that wakes up one morning and marvels at how perfectly the hole in the ground fits its shape. The hole was shaped by the puddle, not the other way around. The anthropic principle may commit the same error. It mistakes the consequence for the cause. We exist because the universe is this way, but why the universe is this way remains untouched. Some proponents argue the principle gains traction only if there is a multiverse, a vast ensemble of universes with different constants. Then our existence becomes a random selection among many trials. But without any evidence for those other universes, the argument is not physics. It is philosophy dressed as a statistical footnote. The upshot is that the fine-tuning problem has not been solved. It has been labeled. The anthropic principle rephrases the mystery. Instead of asking why the constants are so precise, we now ask why this universe, among all possibilities, is the one that contains us, or why any universe exists at all. The anthropic principle provides a framework, but it delivers no mechanism and no prediction. It is a mirror held up to our own existence, not a key to the lock, so the silence from the previous chapter remains. But now we have given it a name. The question is whether naming something brings us closer to understanding or merely provides a comfortable place to stop. What does nothing actually mean? Not the word you use when your glass is empty. Physicists mean something stricter. No space, no time, no fields, no laws, a perfect void. And in the early 1980s, two proposals claimed the universe could emerge from exactly that state using nothing but quantum mechanics. Stephen Hawking and James Hartle offered the no-boundary proposal. Their idea: time behaves like a dimension of space at the universe's earliest moment. If you trace the cosmos backward, instead of hitting a singular point where physics breaks, you reach a smooth, closed surface, like the North Pole of a sphere. No edge, no moment of creation, no before. The question of what happened before the Big Bang becomes as meaningless as asking what lies north of the North Pole. Alexander Vilenkin took a different route. His tunneling model says the universe quantum mechanically tunneled into existence from literally nothing. In quantum mechanics, particles can jump through barriers they classically cannot cross. Vilenkin applied that logic to the cosmos itself, a tiny universe appearing from a state with zero energy, no space, no time. A quantum fluctuation on the scale of existence. Both models remove the need for a creator or a first cause, but here is the problem they share. The nothing in both equations is not the philosophical void you might imagine. It still contains laws of physics, quantum field theory, general relativity, a mathematical framework waiting to be followed. These laws are treated as given, eternal, somehow present before the universe itself. The equations describe how the universe pops into being, but they do not explain where the equations came from or why those particular rules were the ones that wrote reality. That is the gap. Both proposals eliminate the initial singularity, the point where classical physics breaks, but they replace it with a different mystery, the existence of a mathematical structure that precedes existence itself. The silence has not been broken. It has only moved to a quieter room. The universe from nothing, only if you define nothing as something that already contains everything needed to produce a universe. And that definition is its own kind of question. The multiverse is the most seductive escape hatch in physics. If you cannot explain why our universe has the specific laws it does, you multiply the number of universes until our existence becomes statistically unremarkable. The most developed version comes from string theory. String theory requires extra spatial dimensions, and the way those dimensions are curled up determines every constant of physics, the mass of an electron, the strength of gravity, everything. The mathematics says there are roughly 10 to the 500 different ways to curl those dimensions. That is a 1 with 500 zeros. Each configuration corresponds to a different universe, a different set of laws. Our cosmos is just one entry in a catalogue, so vast it dwarfs any number you can name. Now add the anthropic selection step. Across this ensemble, most universes are barren. They fly apart too fast, they collapse too quickly, they contain no stable atoms. Only a tiny fraction permit observers. We inevitably find ourselves in one of those. The multiverse plus anthropic reasoning turns fine-tuning into a sampling effect across nearly infinite trials. The logic is coherent. It solves the problem by eliminating the surprise, but the cost is enormous. An ensemble of 10 to the 500 universes makes no specific prediction about this one. If every possible outcome occurs somewhere, no measurement can falsify the claim. You cannot see those universes. There is no known detection method. The multiverse becomes a metaphysical hypothesis, mathematically dressed, but empirically empty. Physicist Lee Smolin argues a theory that cannot be tested is not science. String theorist Leonard Susskind counters that the landscape is mathematically unavoidable, and we must accept it whether we can verify it or not. This is not an experimental dispute. It is a dispute about what an explanation even is. The multiverse may account for why the dials are set the way they are, but it replaces a mystery with a mechanism that is permanently out of reach. The escape hatch leads to a corridor with no doors. You might assume that after decades of work, physicists at least have a clear path toward a final theory. They do not. The central problem remains unsolved. General relativity and quantum mechanics do not speak the same language. At the Big Bang, gravity is squeezed into a tiny volume where quantum effects dominate. The equations crash. They produce infinities that mean nothing. Without a theory of quantum gravity, we literally cannot describe the universe's first moment. Several alternatives exist. Loop quantum gravity treats space itself as granular, a fabric of discrete loops, not a smooth sheet. Causal set theory proposes that spacetime emerges from a network of individual events, like points on a graph. Both are mathematically consistent. Neither has made a single testable prediction that distinguishes it from the others. They are elegant frameworks awaiting evidence. But even a working theory of quantum gravity would only push the question back one step. It might describe how the universe evolved from some initial quantum state, but it would not explain why that state existed at all. This is where the scientific question collides with something else. The philosopher Sidney Morgenbesser once responded to a similar argument by asking, if nothing is possible, why is there something rather than nothing? His point was that the question may not be asking anything coherent. Nothing, in the strict sense, is not an alternative state. It is the absence of states. You cannot compare something to nothing because there is no background against which to count them. The question assumes a choice exists where no choice makes sense. Physics can trace the chain of causes backward. At some point, the chain ends in a state that simply is. The universe exists. That is the raw data. No equation explains why there is an equation to write in the first place. We have reached the edge of what a scientific explanation can do. What stands beyond is not a theory waiting to be discovered. It is a silence that science cannot fill. Here is what it means to exist in a universe that physics cannot explain. The weight of being a statistical anomaly is not academic. It is felt in the quiet moments when you remember that the laws themselves do not require your presence. The fine-tuning arguments already suggested you were improbable. Quantum cosmology removes even that framework. You are not improbable. You are outside probability entirely. There is no scale that measures your likelihood because the circumstances that produced you have no known cause. That is not a failure you need to fix. It is the actual texture of reality. Scientific humility in the face of deep mystery is the only position that matches the evidence. The physicist Steven Weinberg once said that the more comprehensible the universe becomes, the more pointless it seems. But if the universe is not necessary, then meaning is not a discovery. It is a creation. The silence at the foundation is not a void that demands filling. It is a surface against which every question echoes louder. The beauty of unsolved problems is that they never become routine. A solved problem enters a textbook. An unsolved one stays alive. It changes as you approach it. The question of why there is anything at all has been asked for thousands of years, but each generation asks it in a different voice, with sharper tools and better data. The question does not age. The answer would. No physicist wakes up embarrassed that this problem remains open. They wake up grateful that it does. The edge of the map is where exploration happens. If quantum gravity ever gets fully settled, something else will become unknown. That is the pattern. Knowledge does not shrink mystery. It relocates it. You are part of that relocation. Every time you hold the question in your mind, you are doing what the universe seems to have set up. A piece of itself turning around to look at the whole. The answer may never come, but the space you occupy by asking is the only honest place to be. The space you occupy by asking remains the only honest place. Physics brought us to the edge of explanation. Beyond that edge, the question lives without an answer. That might be its purpose. An answer could end the wondering or rewrite everything, but no answer has come. So the question becomes a permanent part of how you see the world. Thank you for standing at that edge with us. If the question stays with you, write it in a comment, not to close it, but to hold it open. Because if the universe shouldn't exist, and you are here, asking, then maybe the mystery is the point. What now?